Hello, everyone. My name is Rongrong, and I'm a software engineer from Aluxio. And today, want to talk about a story between two open source projects. So basically, Presto and Alluxio, and how the two open source community work together to produce a better end product for the community. So first, let me just introduce myself a little bit. Like, my name is Rongrong Zhong, and I'm a TSC member and committer for the Presto Foundation. I worked on Presto for about 6-7 years now. And previously, I was working at Yahoo and then mostly at Meta, Facebook. And now I joined Aluxio late last year. And if you have any questions, this is my email address. And so if there's anything you want to follow up on, feel free to shoot me an email. And I guess, I don't know how or whether we can share slides afterwards, but my GitHub ID is wrong if you want to check out what I was working on. Yeah, and that's all. Move on to the main topic. So we are talking about Presto and Alluxio. Let's first go over the two projects. What is Presto? Presto originally was developed at Facebook. Now it's called Meta, and it was developed as an interactive analytical query engine as an alternative to Hive. So at that time, the primary query engine in Facebook is Hive, and Hive, as people know, were slow. And so if people want to do some ad hoc analytics and get fast results, Hive is like a painful to wait. So Presto was initially developed as an alternative mostly or primarily for ad hoc queries. So people can get results quickly. And this impacted a lot of the early decisions of Presto, as there's no isolation and it's a hot cluster that's already started. So basically people can issue a query to it and get results within minutes. And the assumption was that if the query failed, it's fine, you can retry because it only takes a minute. So the one thing that makes Presto easy to use and kind of popular in the community is the concept of connector, and you can query multiple data sources through the connectors. So effectively, you can join your data from Hive with a MySQL table in a JDBC with a JDBC connector, for example. And the workload spans from sub-second to hours. At least that's kind of how, in Meta, how we were using Presto for. So from dashboarding to scheduled ETL pipelines. The project currently has about, more like 17K GitHub stars and for almost 5K forks. So it's a pretty popular open source project. And it's deployed in large scale in many of the large internet companies. And then an overview for the Aluxio project. It was originally a research project in UC Berkeley MP Lab. And the convenience it provides, one is it provides a unified namespace across multiple storage locations and systems. So if you have fragmented storage, like you have something on the cloud, you have something on-prem, or you have data from different data centers or different HDFS clusters, Aluxio provide a way to hide the details of your storage and provide a uniform namespace or unified namespace or abstraction layer to the upper level applications. It provides a memory speed access, data access across networks. It provides a caching layer that hosted the hot data in memory. So if you access some frequently accessed data across the network, then you can hit it from the Aluxio cluster, thus avoid the network cost. It has more than 1,200 contributors on GitHub right now. So it's there's a pretty big contributor community on GitHub, and it was ranked the 9th most critical Java-based open source project on GitHub. And this is also in production in large scale in many of the large internet companies as well. So with the background covered, let's kind of get into how the two communities meet each other and start to work together. And so first, some background about the Presto architecture. Presto was primarily developed as a disaggregated or like for disaggregated architecture. Typically speaking, you have your Presto cluster running as a separate cluster from your storage. You can run like Presto on the HDFS cluster, but people rarely do so. Normally, you know, like Hive or Spark, you might schedule it to run as the HDFS cluster, but Presto initially, when developed, was mostly run as a standalone cluster that accesses the storage remotely. So the nice thing about this way of organizing compute is it allows storage and compute to scale separately. So at that time when Presto started, Facebook already started to do the disaggregated compute and storage in our data center. So the compute racks only have compute and storage are in separate racks. That's also kind of like where cloud start to take off, and in cloud, compute and storage are typically separated as well. So this architecture is pretty cloud friendly. It allows very easy like deployment and management and run everything. And then connectors obviously can help you to access any remote data. But it comes with some problems. So one is if your compute and storage doesn't sit inside the same region or in the same data center, then the latency for accessing your data would be pretty bad. And as a result, it's basically not usable for low latency workload. And another problem with accessing storage over a network is the tail latency can vary dramatically. So you probably have most of your query that finishes within reasonable time, but then once in a while you have very slow queries. And it's very unpredictable. So it's very hard to provide SLA on pipelines or on queries. So to address that and to adapt to some low latency requirement workload, Presto developed a connector called Raptor. And it was designed for workload with low latency. And the design decision was basically we're gonna build a storage engine that's like shared nothing. So basically data are stored on the Presto worker node on SSD. And when coordinators schedule the query, it would schedule the split to run on where the data is. So it's kind of like, you know, running on like Spark or Hive schedule to run on HDFS. But instead of running on schedule the compute to run on the data, we just like brought the data onto the compute node. But there are problems that comes with this architecture. So first of all, if you tie compute and storage together, your cluster size mostly, because the data would grow, your cluster size is tied to the data size. If your data doesn't fit in this number of workers, you have to increase the number of workers. Even if the compute doesn't increase, you still have to increase. So like one problem is basically a pretty low cluster utilization because the, you know, if you have more data, you just need to make larger clusters, even though you don't have more use. And another reason that the CPU, the utilization would be low is it's not very easy to use because people have to ingest data into this cluster. So you have to manage your ingestion pipeline. So there is a pretty high operational cost with it. And interestingly, this also gives you a not very predictable tail latency because data are typically only stored on one worker, and if for any reason that worker is slow, then your whole query will be slow. For example, if certain worker runs into memory issues and has to do GC, and there's a long GC pause, and then suddenly all the query becomes slow because query have data that has to process data on that node. And another concern is because there's a separate ingestion pipeline and the data are stored on the worker permanently. So if there's any security and privacy policy that needs to be enforced, a solution has to be built for this cluster separately. At that time, we were like, okay, let's, can we build a cache-based solution? The project was codenamed Raptor X because we want to basically replace Raptor with the, X faster that thing. So it's kind of like Raptor X was not directly related to Raptor, but it's more like a replacement of Raptor situation. So yeah, Presto community at that time want to build a solution that's basically only using the local flash as a cache. So basically data are mostly stored on local workers, but it's only a caching layer. And if the data is not available locally, you can always go to the remote storage as a backup. And that's kind of at the same time when I go to meetups or conferences or talks, I start to hear people asking me about, have you heard about Aluxio? And I was like, what is Aluxio? Okay, and so what is Aluxio? Aluxio was basically, again, like as mentioned before, it's a unified API for storage that you can basically mount storage from different cloud provider or your on-prem HDFS cluster or like many other IO storage. You can mount it to Aluxio, and you can run a Aluxio cluster that's sitting in the same data center as your compute or sitting in the same like proximity to your compute clusters. And you can potentially have multiple compute clusters or compute storage compute engines. And they can all access from the data through Aluxio or from Aluxio. And the benefit of deploying it this way, so basically you have a standalone Aluxio cluster running close to your Spark or Hive or Presto cluster. So first of all, it hides the complexity of the underlying storage, and it actually allows you to, if possible, like migrating data from one storage to another, or like even like, aging out your hot or warm data to a colder storage location without users knowing about it. And it also caches the data close to compute. Here, your remote storage can be in different networks, but then because your Aluxio cluster sits next to your storage cluster, so you can cache data close to compute, and then you can share the hot data among multiple query engines. So normally in analytical world, if you use multiple engines, they're likely to access the same data because, like a lot of times data are daily partitioned. So like hot data, you might have like a Spark producing the data and then Presto consuming the data. So there are data exchange or sharing across engines. So if you have a cluster hosting all the hot data, all the engine can benefit. So the nice thing, but what about the situation when you are running Aluxio only with Presto? So you only have one query. Let's assume like you only have one query engine that is Presto, and you're running Aluxio to speed up your Presto clusters workload and hide the latency from the remote storage. In this situation, you can still deploy Aluxio as a separate cluster, but a lot of the situations you can also deploy Presto and Aluxio co-located on the same machine. So basically, on a Presto worker, you also deploy a Aluxio worker. So and like the nice thing about it is it works, and it also speed up queries. The downside though is like you have to manage two separate clusters, and even though your Presto worker is accessing from the Aluxio worker on the same node, they have to go through the network and everything. Like we can definitely do a better performance or have a better performance than this. And specifically for at that time, Facebook or Meta's use case, the Presto and storage cluster actually sits in the same data center. So running on a caching solution on the same node, but with network overhead is not that attractive as a solution. So that's when like the two community was like, okay, let's work together and get to a better solution. What we did is basically have Aluxio as a library that so basically Aluxio would run as a library inside Presto, and Presto worker would delegate the management of all the SSD to Aluxio, and Aluxio would manage it as a caching space. And Presto still uses HDFS interface, so it's transparent to the engine. And Aluxio cache, in this case, would optimize for small page sizes, and it would only support local access. So basically, no worker can access through network remotely from the cache. The reason we need to optimize for small page access or small pages is analytical workload running on Presto. Typically, the data format are stored in a columnar file system or like file format, like Oracle Parquet, and the data. So the read pattern, because queries normally only access certain columns, not all columns of table, the pattern of reading the file is kind of random with the small chunks. So typically you would first read the file footer, which is the end of the file, and then depending on the footer, you would go to certain like row groups and then read the row group header and then jump to certain columns. So each read is relatively small, and a large part of the files might not need to be read. So if we cache larger chunks, you might be caching data that like actually the engine is not needed. So it's reducing cache efficiency. So on the Presto side, we implement a locality aware scheduling, which means that for any data, you primarily only need to cache it on very few number of workers. That also effectively increase your total like cache size and cache effectiveness. So yeah, so the default configuration of the Aluxio data cache page size is 1 megabyte. It's configurable, and each 1 megabyte page is stored as a separate file. This is like a specific, so this is actually configurable as the type of Aluxio data cache. So if you can choose to cache it as files, and we also support RocksDB now. So you can, but if you choose the format as caching it as files, it would be like each 1 megabyte page would be stored as a separate file, and files are bucketed. So each directory doesn't have way too many files, otherwise it will hurt performance. And it supports high concurrency read, because Presto worker can be concurrently processing many requests and going through many files. So high concurrency read is important. And if the worker restarts, Aluxio will try to recover the data from the cache. So if you have like temporary glitch on the worker went down and come back again, you don't lose all your already cached, locally cached data. It also exports various metrics on cache read hits, so you can effectively monitor it. So on the Presto side, what we did is affinity scheduling. It uses hashing to pick two preferred workers. This is hard-coded right now, but I mean, like theoretically it can be made configurable, but like it seems like two would be a good enough number. So it picks two workers and will try the first worker and to see whether it's busy. If it's busy, then it would go to the second preferred worker. If both workers are busy, we'll just pick a random worker. But data would only be cached on the two preferred workers. So if it goes to a random worker, then the random worker will not cache this data. So this means a data is a piece of data is mostly cached at two workers. And if you like the hashing algorithm, you can choose which hashing you want to use. And for a static cluster setup, it doesn't really matter. Like we normally just you can use a mod, but if you have a dynamic cluster, probably consistent hashing is a better algorithm. So if a worker leaves the cluster, then only the data on that worker needs to be reshuffled to other workers. Yeah, so, and this makes the cache efficiency better because each data is at most cached twice. And so your total cluster size divided by 2, probably larger than that, is your effectively the amount of data you can actually cache. So here's a benchmark on running Presto with the Aluxio local cache. You can see that, so the numbers are like query latencies. You can see that with caching, latency improves, and especially the tail latency improves a bit more than the mean and P50. So RaptorX is basically a Presto with Aluxio managing the workers SSD as the local data cache, and also includes some other metadata caching on the coordinator side, because when we run the planner and optimizer, we need to access the metastore, and for scheduling we need to list the files and schedule splits. So these are also cached. File descriptor and footer cache is also to reduce, because like basically every read needs to get to read the file footer first before they can know where the data is. So so like caching the file footer is pretty efficient. So basically after RaptorX, the two communities kind of like see the benefit of collaboration. So we continue to collaborate on more features along the line. So one problem that we're trying to solve is how to estimate working set size. So basically, if you are thinking of like, do I have enough caching to cache all the all the hot data of my workload? How big a cache do I need? So like, then how do I know about this, right? So the challenge is we want to be able to figure out the working set size while running the workload. We don't want to like run the workload again in some offline cluster to gather metrics. So we want to gather the metrics online. And because we're trying to gather the metrics online, we want a low CPU and memory overhead solution. And we also want to support sliding window because, like queries normally are analyzing data of this day or of the last 7 days or something like that. So, or like, aggregating over a month, but like it's normally analytics query are time-based. So we want to be able to say like, what's the working set size for workload for a day or for a week or for like a month. And it needs to be accurate enough, like if it's like a random guess, then like it's not really an estimation. So the solution we build is a cuckoo filter based shadow cache. So basically, when you're accessing data, we track data access as an insert to this cuckoo filter. And there's also a clock field added to this cuckoo filter to track when is the last time a certain data is accessed. So cuckoo filter is basically a hash-based solution that on each hash entry, you have a few kind of slots. And within each slot, you're storing the fingerprint of the data rather than the data itself. So it's like space efficient. And here we also are storing the clock and size and an optional payload. Size is basically how big the data you're accessing, and clock is the last, basically the latest access time. So there's an aging process. Basically, periodically, you would just decrease the clock counter. And once the age reaches 0, you can clean up this entry from the hash table. So this way, for example, if I want to see what's the working set size for the last 7 days, and each data access would insert an entry to the hash table, and every day you can age out, like decrease the clock by 1 basically. And then 7 days later, if nothing was accessing the data within the last 7 days, the counter for that entry will reach 0, and you can clean it up. So by checking the size of the cuckoo filter, you can get an estimation within error bound about like how big your working set size is. So based on the results of your shadow cache and the results of your actual cache, you can basically know about your workload. So if your shadow cache hit rate is low and your cache hit rate is also low, that basically means this workload is not cache friendly. So a lot of the ETL pipelines that maybe process the data only once, but then the data was not later used, then the data is not really, caching it doesn't really help your later workload because there's no repeated access for the workload. But if your cache hit rate is low, but your cuckoo, like your shadow cache hit rate is high, that basically means you should probably increase your cache size, or increasing your cache size would improve your overall performance. But if both are low, then that, or like both hit rates are high, that means you might be over provisioning your cache, and you probably don't need that many cache. You can shrink your cache size and free your SSD for something else. And there's another solution that we built between the two communities, which is when you have very limited cache size. So estimating working set size is when you have enough caching capacity and you want to know how big your cache should be to give you the best performance. But on the other hand, if you know that your cache size is limited, you only want to cache the hottest data, then how to do that? Our first solution is to have a configurable cache filter, because a lot of the times the people who are managing the clusters actually have information or have knowledge about which data are accessed more frequently. So if you just allow people to easily say that, these tables and these partitions are cached and others are, please ignore them, then that's like an easy solution to build, to configure how to effectively use your cache. There is later work that we're currently working on, which is you can basically base on your shadow cache results to automatically decide which data needs to be, which data should be cached and which doesn't need to. Yeah, so let's see some of the uses of this solution. So first, the project was first developed, or like the two community worked together for a specific use case in Facebook or Meta, which is to build a cache-based solution to replace Raptor. So the previous workload running on Raptor, which is first is a A/B testing framework. And another wide use case is basically dashboarding. So people want to cache data or like for faster results when they want to build dashboards. When we migrate the workload from Raptor to RaptorX, it basically allows the compute to grow multiple X while retaining the same cluster size, because now we don't need to guarantee all the data are sitting on the cluster, like only the hot data are on the cluster, and you can always fall back to compute. So now you can allow compute and storage to scale separately. And another reason I think for the fast adoption, or like the fast growth on compute, is also now people don't need to worry about injecting data into the cluster, so they don't need to worry about capacity and provisioning and everything, and they can just start using it. It kind of just works. This was also enabled like opportunistically on the interactive analytical cluster. So basically, for any ad hoc queries, the cluster come with caching as well. This is also running in production in Uber, and some of the features we developed in Cache and in Presto are collaboration with Uber. Uber has the situation that not all machines have caching, so they do have a limited caching capacity issue, and their clusters are dynamic. So basically, workers can come and go. I think they have a cloud deployment. So basically, workers can come and go like randomly. So making sure that the hashing is stable, and when the worker leave the cluster, not all data are reshuffled is important. And another thing is Uber uses Hudi, which supports upserts. So the data are changing very frequently. And the solution we have is basically using the cache filter to only cache the hot data, consistent hashing. And then when we schedule, or when Presto coordinator schedule splits, instead of just using the file path to choose the worker, we use file path and last modification time. So that way you would also hit the latest partition. And the latest partition will be cached. If it's not cached, it will be fetched instead of using older partition. As you can see that, collaboration actually makes both projects better. So for Presto, working with Aluxio means that, instead of building like, we're query engine folks, like not needing to worry about how to build a cache is good. So someone else help us build a cache solution. And collaborating with Aluxio basically means that, we actually launched RaptorX into production within a year. If we have to build the whole solution ground up all by ourselves, it'll probably take a bit longer. And for Aluxio, it also means that we get the opportunity to have a better understanding about the use cases and the workload, and we would have a better understanding of what kind of feature or optimization we can do in the cache or in the caching layer to speed up the workload even more. So the end result is basically like a better performance for the user that uses Presto and Alluxio at the same time. Yeah, so there are some ongoing and future collaboration ideas. So first, file metadata caching on the Presto side are right now in memory only, and we want to persist it as well. So, if a worker restarts, you can recover the file metadata as well. And we want to have table level caching metrics. This will guide us to better choose which are more effective, which tables are more effective to cache. And cache rate limiting is kind of like a solution to help, I guess, not wear out flash too quickly. So if you just keep if your working set is bigger than your cache size, frequently evict based on shallow cache and semantic aware caching. Basically, things like, specific for a file format, you want to potentially cache column row groups or cache certain columns only, and cache data uncompressed instead of like caching just the file segment. And then a native cache client library for C++, because Presto is having Velox is working on Velox as a C++ native worker. So for that solution, have a C++ caching client would be very useful. Yeah, that's all. Thanks. Any questions?
So I have one question. How would you compare this solution or the with some other players in the market? So basically think on some like if AWS has its own solution for distributed storage. What are the key features that maybe differentiate Presto from Aluxio in this case?
So Presto is a query engine, and Aluxio is like file system level abstraction right now. So they kind of like are operating on different layers of the stack, and that's why combining the two together kind of works for both. And I guess like if you talk about the Presto competitors, you can have Athena or as like I guess Spark is another query engine, and the cloud solutions would be like Snowflake and stuff. So specifically about Presto plus Aluxio, I think the advantage is it gives you the benefit of both a disaggregated compute and storage cluster, and at the same time the speed of co-located storage and compute. So I guess another solution that's popular in the market is ClickHouse. ClickHouse is a compute and storage co-located solution, right? So like you have data and compute is running on where the data is basically. And these kind of solution actually this suits better for really low latency query workload. So if you want like milliseconds or like sub 100 millisecond work efficiency query latency, then those are probably a better solution. But if you're in the second-ish or like a few seconds range, then those solutions, like if you have a co-located storage and compute solution, typically you're kind of like you either have to pre-compute and pre-aggregate and only put your aggregated table inside this, which added overhead to development and maintenance, or you potentially can have more data than what you absolutely needed, and thus you have to run a cluster with a pretty low CPU utilization because your data fits. You need more machines to host your data, but then you don't necessarily need that many compute. So this is kind of a solution that if you don't really require really low latency, like sub 100 millisecond, you can kind of get the benefit of both worlds. You can, for your really frequently accessed data, get the speed of running on a local storage. But then if you're accessing a data that doesn't sit in your local storage, your query still runs. And you don't need to worry about like ingesting your data into a different storage system or different compute or like ecosystem. Your data is just where your normal, warehouse data sits. Does that answer your question?
Yes, perfect. Another follow question. Does the caching level is on the, let's say, on the file system level or on the block level? Maybe you addressed this in the slide, but I was not I was not having the proper attention. But is this in the block level or on the file system level?
What do you mean by block level?
So let's say it's basically more low level on the, disk level, this block level. Yeah.
Caching data on 1 megabyte chunks. So it's actually smaller than typical distributed file system block size. I think typically the block size would be like 64 megabytes or something like that. Like it's just, like block size are typically larger for file systems. But we are catching data with a smaller size because columnar file systems, the structure of columnar file systems is data are broken into row groups, and within each row group, data are stored by column. And analytical queries only access very few columns out of a table. What that means is it's kind of reading like a sliver of data across the whole file, but it's like jumping, because like your file would be like this, and then data are stored in row groups, and within row groups is columns, and you're only reading this row group on this part and this row group on this part, right? So each read is actually relatively small. So that's why we're storing, we're actually breaking the file down into very small chunks. So we only cache the data that's actually used.
Nice, thank you.
Ladies and gentlemen, any other questions before we wrap up? Okay, Rongrong, I want to say very, very thank you for your lecture, your time, and your patience. I learned a lot from this lecture, and I hope we can work together again with this community in the future.
Thanks a lot.